Hey guys, remember this device? This is the Graphical LCD screen that I used in my last video to render 3D wireframe 3D rotations. And that was all fantastic, but there was one thing that was missing that I didn't complete. And that is this screen can also be connected using serial communication. And on the back here, you have this pin here, PSB. And in the last video, I set it to parallel using all these data lines. But in this video, I'll be going through how to use this screen in serial mode on the Z80. So let's get started. So which pins are actually used for the serial connection? It doesn't really say in the datasheet that I have. So I have to go to the actual chip, the ST7920 datasheet, and it explains that RS pin is also the chip select. The RW pin is the serial input data line, and the E pin is the serial clock. And the datasheet also contains a fairly good explanation of how to connect the LCD using the serial interface. It talks about setting up the chip select line, but because we're only using one connection, the chip select line could be pulled high, so we don't need to select multiple devices. And let's have a look at the timing diagram. And it uses the SPI protocol, where the serial clock is triggered by the CPU and 3 bytes of data are to be sent. First, to have a synchronization byte, which contains 5 ones, a read-write option, and a register select. But transferring in serial mode is only writing, so this value here will always be 0. And it's just a matter of toggling the register select, whether it's data, that will be high, or whether it's instruction, that will be low. And that's 1 byte. The next 2 bytes is the information that you would like to send, but split into 2. So essentially a 4-bit transfer. It doesn't say specifically here, but these bits are recognized when the clock is high. So let's now implement this protocol on the Z80. So let's firstly see how we can wire the LCD screen using the serial connection. So you have the 20 standard LCD pins, then we add the usual suspects, ground and 5 volts to power and ground, reset from the CPU and backlight, power and ground. And 3 of the pins aren't connected at all. Now we set the P and S pin, the parallel and serial pin, to ground. This tells the LCD screen that we are going to communicate using the serial lines. And the 3 serial lines are chip select, serial input data, and serial clock. So the chip select line can just be tied high because there is only one peripheral, which is the LCD screen. But we need to protect the data lines from the data bus of the CPU. This is where we can use 2 D flip-flops to latch the data line data to the LCD screen. So the Q line is just connected up to the SID and the serial clock, and then any particular data line, I've just chosen D0, which will make coding a bit easier for the SID line. That connects to SID, and D1 to the serial clock. And then lastly, we connect the port line to the clock line of the D flip-flops. So how the flip-flops work is on the rising edge of the clock, whatever's on D1 or D0 will get copied to the Q lines, and that stores that value until the next clock signal goes from low to high. And this isolates the LCD from the data bus. So somewhat a much simpler setup with less lines used. Only 2 data lines are needed to make the serial connection work. So here is the PC board that I designed and produced by the wonderful PCB Way, a very high quality end result. It's a bit of a all-in-one board, and it's really overkill for what I really need, but you can connect the LCD via serial or parallel. It also has its onboard port decoder and the ability to turn on the backlight and also a contrast trim pot. And thanks again for PCB Way for sponsoring this video. They're a fantastic company. I highly recommend ordering your PC boards from them. Have you been dreaming of that electronic project and want to make it a reality? Just like my ultimate expansion board for the TEC-1F. Well, head over to PCB Way to make your dreams come true. PCB Way are the leading printed circuit board manufacturer. They make high quality multi-layer boards with a 24-hour production time. Just enter the board dimensions and upload your Gerber file, and that's it. Once posted, a neat box will arrive with your well-packed goodies. Just look at the quality of this board. They also do PC board assembly, CNC machining, and 3D printing. You can even order user project boards directly from their website. For $5 off your first order, click on the link below. PCB Way, prototype the easy way. So here is my setup, the usual suspect, the Talking Electronics TEC-1F, connected via this expansion board that I created through an IDC cable into the PC board for the LCD screen. And over here I've got my serial connection so I can transfer all the code from my computer to the TEC. Let's now have a closer look at this PC board and get some graphics displayed on it. So with the jumpers here, I have it set up in serial mode, selecting the PBS line to serial, and also flicking these three jumpers to the serial side because I've got the three serial pins to connect. I'm also using on-port decoding here, so it's going through port OB. With the backlight, you can turn on and off, you can see that. And these screens auto contrast, so I don't really need a trim pot there. In order to send data serially to the LCD screen, we need to consider three factors: the data lines 0 and 1 and the port. I've connected D0 to the serial input data line and D1 to the serial clock. And we need to send only bits of information of each byte. I have a routine here called SPI write, which takes in one parameter, which is the A register, the byte to send. We know we have 8 bytes to send, so I load the B register with 8, and I'll also save the actual byte to send in C. I clear out A, XOR A means load A0. I rotate the bits of register C, which is the SPI byte, by 1, and RLC C would actually put bit 7, the first bit, into the carry flag. And then I do an add with carry A and A. Now, it's a bit weird, this one, adding A and A, but all this does, because A is 0, is like doing a load A to carry. And that sets up my D0 bit. Then I set the clock high by doing a bitwise OR with 2, D1, or setting the second bit. Now I've got the clock high and my value set in D0. I just output it now to the port. This will then latch it onto the D flip-flops and send the bit. I clear out A again because now we need to set the clock to low, and we don't care about the serial input data bit anymore, and then we just output it back to the LCD screen by having a low clock. And then we just loop again 8 times, so DJNZ will decrease B, and if B isn't 0, it will loop back to clock loop. We'll rotate the next bit across to the carry flag and repeat the process, and this sends all 8 bits out to the LCD screen. But we're not just sending one byte of information, we need to send a synchronization bit, we need to send the data bits. How do I achieve that? So I have two methods, LCD instruction and LCD data. LCD instruction would firstly send the serial synchronization bit. All I do is OR the register A with the default serial byte, which is 5 ones, a 0 because we're writing only, and by default it's an instruction byte, which will have this bit set to 0. And then we just fall down into the SPI write routine. Alright, what about the data? I call jumps to serial byte. Looking at the specification, we need to send 2 bytes of information where the high nibble contains the relevant information with trailing 4 zeros, and we need to split the byte that we want to send into 2 bytes. One byte contains the high nibble, the next byte contains the low nibble. Okay, so this routine takes in 1 byte, which is what we want to send. We firstly save that byte to the stack because we are going to override it temporarily, and we're going to call send part. What does send part do? It does an AND with OF, which masks out all the lower bits, D0 to D3, makes them 0 and keeps the high bits the same. Perfect, this sets up our first byte. And then we just call SPI write, and that will send that out to the LCD. It will return back to here, and we pop AF because we've destroyed AF. We need to restore it to the original byte. And now we do 4 rotate lefts, which will shift the 4 lower bits to the high order bits, and then we just fall through down to the send part routine, mask out the lower bits because we don't care about them, and send it across. And I jump here because eventually the SPI routine will do a return, and it will return back to my original calling method, which is the LCD instruction, and it will return back to whichever routine called this LCD instruction. What about writing data to the LCD? It's effectively the same, but what's not obvious here is that when you do send a synchronization bit, you don't need to keep sending synchronization bits for every byte we're sending. We only need to do this synchronization bit once, and we can send up to 256 bytes of data in this 2-byte structure here. So for sending LCD data, it's recommended to call serial byte separately to do it once, and then loop through all the data that we require to send. So it's connected up now to the serial connection using the 3D wireframe rendering that I wrote. Let's give that a go. And let's start rotating the shape. And you can see here the serial connection is a bit slower than the parallel connection, and that's obvious. There's always trade-offs between how many wires to use and the speed of the data transferring across. And this is as fast as I think I can get it at this stage at 4 MHz. Let's now do a comparison with the parallel connection and see the speed difference. And you can see it is a lot slower, but it depends what you have. Unless you might only have a few wires to use, so serial will work, but if you've got the all 8 data lines, then this will work perfectly, just using parallel. Now I have my serial interface working, I was thinking about what should I write next. My first job was working on a VMS Alpha at an insurance company, and I used one of these terminals. And it was a great job, but occasionally I was a bit bored and I wrote some games just for fun. And one of the programs I wrote was this maze generation program. It was written in DEC Structured Basic and used ASCII characters to render the maze. One of my favorite maze generation algorithms is the Recursive Backtrack algorithm. So I quickly whipped up a prototype in C++, and this is the result. It looks pretty cool. It uses a stack to remember the last cell locations, because once it runs out of walls to push through, it will need to backtrack back to the last unchecked cell and keep carving walls through unvisited cells. It looks pretty cool. It's not the fastest algorithm, but it's somewhat beautiful to watch. The blue squares are cells that have been visited, and all adjacent walls have been visited, and it ends by going back to the start. Now, copying this from C++ to Z80 assembly was a bit of a challenge, and what you see here is the final result, but it took me a few iterations to refactor the code to make it a lot faster. So let's go through that journey. Let's step through how this algorithm works in creating the maze. Firstly, we pick a starting cell. For this case, I picked A1, top left-hand corner. And we randomly move that cell, or the current cell, to another adjacent cell which hasn't been visited yet. We now move that to B1, and in doing so, we remove the walls between A1 and B1. And the routine just continues on. Let's find another random cell that hasn't been visited, C1, and again move to another cell, C2, B2, B3. Are there more available cells? Yes, there are. C3, D3. Any more adjacent cells? Still some more to go. D2 and D1. Each time we're adding the previous cell to the backtrack stack. And this is because when we run out of cells to move into, there's no adjacent cells that haven't been visited, or we're not at the boundaries of the maze. We need to work out where the previous cell was. So to do that, we just pop the top element off the stack, D1, and make the current cell the previous cell, which is D2. Any available cells remaining there? No. So we go back to D3. Again, no available cells, adjacent cells. We move to C3 and then B3. But here we do have a new adjacent cell that we haven't visited. So we continue the algorithm. We add it to the stack, A3, and one more cell hasn't been visited, which is A2. Now all the adjacent cells here have been visited, so we just backtrack to the previous cell. And we do that check again. But as you can see, all the cells now have been visited. We keep backtracking back down to the start. And when we've got to the start and there's no more adjacent cells to be added to the stack, we pop the last element off the stack and
we're finished with the algorithm. So the biggest challenge with writing this code on the Z80 wasn't actually coding it and converting it from my prototype example in C++ to assembly. It was actually the program design. So when I initially designed the maze algorithm on the Z80, when I ran it, it was extremely slow. In fact, embarrassingly slow, and I couldn't show this to you guys. So I had to figure out ways to make it a lot faster for the hardware and the language that I'm using. In the C++ example that I wrote, you can be really lazy with the coding, and I effectively tried to mirror what I did there. It just wasn't good enough. So this was my initial design. I have one cell, and each cell has got 4 sides to it: a top, a bottom, a left, and a right. Then I multiplied this cell by the X and Y boundaries of the LCD screen, and I created an array of cells. So each cell has 4 walls, and then I drew the screen. So each of these cells, I was using the Bressenham algorithm just to draw the straight line, up, down, left, and right, for each cell and each border, and I was doubling up with the lines because each adjacent cell has an overlap of their walls. And then I would move the current cell to the next cell and destroy 2 walls and redraw the whole screen again and the graphics buffer. Another 2 walls removed, redraw all lines again to the graphics buffer, and then plot it to the screen. Another wall, another wall, another wall. And I was doing this over and over again. This was just highly inefficient. What a crappy design. So after a bit of tinkering, this is what I came up with. You know, it might not be the best design, but it's pretty efficient. Instead of having 4 walls, I just need 2 walls. And as you can see, if I lay out the cells next to each other, it actually completes a similar grid. Apart from the bottom line and the rightmost line, but we can just draw them directly to the screen because they would never be overwritten because they're on the boundary. And drawing these lines, I don't need to use any complicated line algorithm. I just need to draw straight lines, which is really simple to do. And on top of that, I only draw it once to the screen because all I need to do now is remove some pixels from the screen. In fact, only 5 pixels I need to remove for every wall removed. So I remove the 5 pixels from the graphics buffer only, and then refresh the screen. Another 5 pixels, and keep going. Just by this simple design change, made the algorithm work much faster. So I won't go through all the code, but here are some of the highlights of how I got the algorithm to work on the Z80. Drawing the current cell on the screen, or something that looks like a cursor, this is how I wrote the procedure to draw the current cell on the screen. Firstly, I get the current cell location in DE, and then I convert it to pixel space. So now BC is the actual pixel location on the screen. I increase B and C because I wanted to make it within the boundaries of the 5x5 cell location. So now it will be a 4x4 cell. I set D to be 4 because I'm going to draw 4 lines. And then all I do is at the location BC, I flip the pixel or invert the pixel. So if there's no pixel present, it will be displayed. And if there is a pixel present, it will be removed. And I do this 4 times, increase to the next column, and do all that 4 times. But the clever thing here is that I just need to call draw current cell whether I'm removing or adding the cursor. So this is a clever way to add and remove moving objects onto the screen. So here's how I've implemented the backtracking stack. So this is my pushing routine, pushing onto the backtrack stack. This is just the current address of the top of the stack. I put into HL. I decrement it because traditionally stacks actually go downwards. DE is the current cell that I want to push onto the stack. I store D, I decrement HL, and I store E. Now we've got a new HL, I save the current top of the stack back into the backtrack. Pretty straightforward there. It gets a bit more complicated when you're popping off because you don't want to just keep popping off nothing. We want to know when the end of the stack is reached. So firstly, I get the stack address and I initially just pop off the first two elements because we actually don't care about the current cell anymore. We want to look at the previous cell. I'll put the new top of the stack into DE, and I'll make HL equal the initial start address of the maze stack, but a negative of it. So when I add HL and DE now, the current head of the stack, to the base of the stack, if it's in the negative, we've popped the last element off the stack. So I just return carry. And that's something the calling function here would need to manage and say if carry is set, then quit the program. Otherwise, I want to return the new cell value, which is at the top of the stack now. So I just, again, swap HL with DE so I can get the correct head of the stack. I load E with the contents of HL. I increase HL. I load D with the contents of HL. But we want to point the head of the stack back again to the actual head now, so I decrement it back and save it. And that's the pop routine.
So the code's been done. I've connected the LCD screen up. Let's now generate a maze. And there you have it. It's working away using a random sequence to create a path. And it's coming back now here. Eventually, it will get to a point where there's no more available cells adjacent to it, and it will start heading back to the next available cell. It looks pretty good. Fairly happy with this. Now it does take maybe a couple minutes to actually generate the maze using this animation style of way of generating the maze. So here we go, it's going to backtrack now. Last cell, it's going back, perfect, to that cell, to that cell. Now it will come down to here and start digging through the walls. It looks clear, pretty happy with that. Okay, now it's actually locked itself into this corner here. So eventually it will fill all this area up. There we go, it goes up. Okay, we've got a few more cells left. And you can see now it's backtracking back to another free cell, and it will just keep generating the maze. So I'm pretty happy with that. It's a bit slow with Serial, but it's quite interesting watching it do its stuff and create its maze. You can probably watch this for, well, almost hours and see where it goes. Let's now fast forward the maze and see what happens right at the end. Okay, we have a few more remaining cells to go. It's coming back now. We'll go up to this path here, fill out these 6 cells in a random way. There it goes. Now all cells are complete. To finish now, it has to go back to the start of the maze, which is the top left-hand corner, but it could be any position. There we go, a couple more cells actually, and it's heading back to the start. And done. It's over. Let's now see how fast the code is actually generating the maze without the fancy animation and the moving of the current cell. So I've removed the option to plot the screen on every movement of the cell. I'll just do it right at the end of the maze generation, and remove the need to update the cursor. Let's give that a try. There you go. Probably took about 1.5 seconds to generate a new cell, and part of that is just the refresh of the screen. You can kind of see the serial connection fairly slow, but unlimited mazes generated by the TEC-1F on the Z80. Pretty happy with this project. Finally, let's see how fast we can generate this maze using the animation component using parallel mode. I've connected the board using the parallel jumpers for the parallel interface, and let's see how fast this maze can generate. Wow, look at that. It's flying along, generating that maze in a random way. That cursor is going on and off extremely fast. You can't even see the cursor, it's moving so fast. Wow, it's been a really fun project. There's something I've always been fascinated with, maze generation, and I think this recursive backtrack algorithm is pretty cool and really happy with the results. So I guess the next thing is, now I've got the maze, the next thing is to write a maze solving algorithm. I'd like again to thank PCBWay for sponsoring this channel, and I hope you enjoy this very niche retro channel on the Z80 microprocessor. I'll probably have a little break from these videos as I'm working towards writing a new monitor for the new TEC-1G and some other projects. So on that note, see you next time.